Welcome. You are at Databases at Scale at Square. I'm Emily, and I work at Square. I work specifically on the database team within Platform Infrastructure Engineering, acronym for PI. And the talk is going to cover the philosophy, not so much technical details, but the philosophy behind we design our tools and our infrastructure. Oops. It's not advancing. Crap. Hang on. Okay. Square. So a little bit about Square. Square is built as an honest financial network for everybody. So where perhaps there's not much access to banking, there's Square. That's the current philosophy. It is global. We're in the US, Canada, UK, Japan, Australia. We store payment transaction data in MySQL, so we take security super seriously and data consistency super seriously, and downtime. That's a big issue. Whoa, I hit the thing. Wow. And then, of course, we're hiring. There's many positions beyond the database team if you have other interests. And so you may know us from these pictures. From our baby early product, which is the Square Reader, to a better version where you can pay with your phone tap, or a dip, or a tap, or whatever. And then there's the terminal that you might see in coffee shops. And fun story, I didn't even know I was using a Square product, and the Cash App apparently is a Square product, and it's one of our other things that we support. So that's what our databases are doing. By the numbers, these are rough numbers, and let's see, we have over 6,000 unique MySQL nodes. We also do a lot of Redis, so that's about 1,000 of nodes. We have a 99.95 SLA. Our uptime number is actually quite a bit better than that, but that's all that we have to meet, which is 43 seconds of downtime a day. 1 petabyte of data, unique data. So within our topology, which I'll cover, there's replication and stuff, so that's just the unique figure. And stripping out bin logs and stuff like that, that's just what's stored for MySQL. We have about 800 physical servers. We're a 100% Docker shop. We run anywhere between 1 and 20-something Docker containers on a host. We used to use LXC, and we're kind of forced to upgrade to Docker, and it's actually much better for our performance. We can fit a lot more. So the theme of the talk is pebbles, not boulders. I can't say that as well as my colleague with a deep voice that said it once. So pebbles, not boulders. Come on, X. There we go. Small things are much easier to operate on than big things. We apply this theory to everything we do, software design, architecture, operations, and the philosophy is really critical. I was at Square. I've been at Square for about a year and a half, and I was actually really reluctant to join. I remember somebody from Square had approached me like 5 years prior at Percona Live, because I'm kind of like a polyglot database person, and they wanted one of those. And I just flat out said no, because it's financial data, and it was terrifying. But with this philosophy and the team that we have, it's actually the most stress-free job I've ever had. So anyway, yeah, managing anything to do with money sounds stressful. And the way we do it is so simple and agile that it's really not a big deal. Let's see. So yeah, for everything we do, it's pebbles, not boulders. I can manage pebbles. I cannot move that boulder. So managing over 6,000 MySQL and Redis databases would be pretty unwieldy. if they're not all nice, small, uniform rocks. And that is how we keep all of our tools just doing small units of work. So beyond the databases, the tools are just doing a little bit. And it's easy to find failures. It's easy to stop processes. It's easy to do many things at once with that theory. So in terms of databases, pebbles, not boulders, these small little databases that are restricted in size, in disk, and in memory utilization are much easier to deal with than that monolith. We've all had jobs with dreadfully giant databases at some point, and there's that database that everybody is afraid to touch. There's actually a coworker in here. I'm going to tell a story about that soon. So yeah, this is before that job, though. Don't worry about this story. Don't try to place it. At a previous job, I was once tasked with moving a large database from Amazon into this super private data center in England, and I didn't have access over networks, so I had this really messed up SSH tunnel that went through my laptop because I could get to both places, and then to the data center. So then I'm transferring the databases, a backup, and then once the backup is transferred, I also have to replicate and get it back up to speed so that I can cut over. And the perilous thing was that the VPN cut out every 3 hours. So I had a timer, I didn't sleep for more than a 3-hour shift for over a week. And that is, why big databases are bad. It's much easier to translate. I couldn't even eat vegetables for a week. I was so messed up. So I really have a big hatred for that whole thing. And then another time, I had this giant database that Pim knows about, and somebody had crashed it during a MySQL upgrade. It filled up, went corrupt. The replica was corrupt. So I spent an entire weekend massaging the database back to be functional. And people knew it was a problem. They were like, oh, I'm trying not to say the names. It doesn't matter. Nobody knows. Dead 34 and Dead 35. That runs blah, blah, blah. It's huge. It would be, I'm sure somebody said it would be terrible if that crashed, because they couldn't even make backups because it would lock even with extra backup. So it would be terrible if that crashed. Sure hope that doesn't happen. It's running in Amazon. Likely it's going to crash. So nobody actually took that thought further and said, let's try and break it down before it gets too big. So anyway, not my problem anymore. Everything is nice, nimble, and well protected at my current job, and we will get into that shortly. Let me just see if I can move this in a moment. Okay, so now I'm going to get into how we achieve that. These are the topics we're going to cover. So in all the topics, you'll see the theme there that we keep it simple and predictable. And I didn't think things would be so simple at Square, but it really is. So getting into setup and replication, I'm going to do a quick overview of the standard database cluster at Square. And it's this topology on which everything is built, and it makes everything subsequently easy. So this talk will cover both our Redis and our MySQL. The only difference here is you'll see there's a different order, like there's not bidirectional replication for Redis. I tried to make that obvious with the little red cube. Anyway, the dolphin is MySQL, and the red cubey thing, Redis. So this is the standard 4-node cluster. It is data center separated, so you see US West, US East. That's one division. There's an active side and a passive side. The A side there would be considered the active side. The red indicates read-write. Everything else is read-only, super read-only in that set. And basically, the 1 and 2 nodes are, for MySQL, they're co-masters. Only one node is ever writable. well, only one side is active. And the inactive side is where we do all of our operations. So upgrades, config changes, it's just a standard formula, like push out a change, do it to the inactive side, fail over, the formerly active side becomes inactive, and we work on that one. The clusters are numbered and application specific, so a cluster only is going to be for one application. And applications will have multiple clusters because you'll see it has to do with our size limitations that we kind of enforce. And so, not too long ago, like 2 years ago to be exact, our setup of this standard 4-node cluster was done by some Ruby scripts, I believe, and it was awful. Like sorry to say, it just was failure prone. Sometimes the containers would come up, sometimes things would be, but there wasn't enough error checking. So we spent a lot of operational time just provisioning databases because there are a lot of databases. And the scripts failed often, they took a long time to run, and we built a platform that automates that tedious task. Ta-da, spin cycle, which we recently open sourced. I'll have the URL up there in one more click. But at first, it's only like, its primary focus was fixing that making the 4-node cluster. And then we've built on it because it's been so reliable for us. But yes, that's on GitHub. And so I don't think there's actually any Bash or Ruby scripts I do for regular operations anymore. It's all spin cycle jobs. So our spin cycle jobs are used for provisioning, Redis and MySQL upgrades, config changes. So like I might set, change the InnoDB buffer pool. That's done through spin cycle job. Does all the appropriate steps. OS upgrades. We have another system that manages the whole chaos of an OS upgrade, but it calls to spin cycle to do its work. Spin cycle is the worker bee. And deprovisioning. So of course, applications, let's say somebody spins something up for Hack Week at your company. This system also does the deprovisioning, which was once like a Ruby script or a Bash script. So it was a big success. And we're able to automate things because everything looks the same. Everything is a 4-node cluster. And pieces are small. Let's say we had a giant database. It would be a lot harder to fail over that giant database. It would take time. Replication might be laggy. So we keep it small. So there's the URL for spin cycle. And let's see. So the next topic is high availability. The standard 4-node topology makes it pretty easy to maintain high availability. So this is how, I'm going to run through how we do maintenance on one side and then flip over or fail over for other reasons. This is the normal state. Only one is read-write. And there's a VIP that we have attached to the read-write node. And then there's a read-write CNAME. Our application owners use the read-write CNAME. So their application is only ever pointed at that. That doesn't change. And to fail over to the B side generally takes about, there's about half a second of downtime. There are pre- and post-flight checks, some sanity checking, and let me just walk through that process of failing over to the B side in our topology. Oh, and so the VIP is data center specific, so that I'll get into that with the data center failovers. But the CNAME is just a global address. It could point anywhere if it wanted to. So the first step in our failing things over is we just simply turn the read-write node to read-only, and we remove the addresses. So the VIP gets detached, which basically makes it so that the CNAME, that the application owner, they don't have anywhere to go anymore. So they'll have a couple of connection errors. And then, it's gray, so it's clearly read-only. And let's see, the next step is we flip the VIP, or we bring it up on the O2 node. And so now the read-write CNAME has somewhere to point. And we've made it read-write. And while this is happening, we kill connections, the lingering connections that might be on the one node. The application will reconnect during this. And again, the total downtime is about 500 milliseconds to a whole second. And when it's done for maintenance, we call this a success over because nothing has technically failed. I'm not going to have Brian tell the joke. Next one. Okay. Nothing has failed. So we use the term success over a lot because if you heard that you were getting a failover, you might have a little bit of panic. You can use that too. It's fine. Yeah, I think actually I Googled it, and I think YouTube used it for a little while. Yeah, so it's free to steal. And so success overs are super common, like everything we're doing. And applications are supposed to anticipate that success overs could happen at any time. So they also have to go through the whole testing process to make sure that they are ready to, they don't have anything hard-coded, they don't have anything too sticky. So they have the ability to do this process on their own. We have an API that they can call to test it with their application. And we do this constantly with our spin cycle tool. And so we do work on one side, flip it over, do work on the other side. It's pretty easy peasy. So back to normal. So in this case, not back to normal. In this case, let's say an entire side dies. This is highly unlikely that it would look like this, but let's say either one of these died. So we tend to not clone, and the clone is basically we spawn a backup and then reload it on the newly born node. We tend to avoid doing the cloning from the active. So you'll see the weird string of the way things happen. So if 2 were to die, we would opt to probably clone it from 3 in this scenario. If 4 were to die, we would elect to do 2. Because that kind of it's the laziest way of doing it. Your replication is probably all set, and at some point we didn't have GTID. Some of our clusters still don't have GTID, but this is the least amount of steps. So after rebuilding, we restore. There's no replication chain shuffling, and everything is back to normal. So let's say a data center dies, which does happen, and we do run through disaster recovery tests. Each application is mandated to test running out of the other data center. So they generally have the keys to do this. They are not blocked on our team at all. They can just initiate the data center failover. So anyway, let's pretend data center at the top died, and it comes back up. It's just as easy as cloning from, this is the least center. So let's just say this is up. Because the most sensible way to do this would be to take from 4 and build 2 and then clone from 1, or clone 1 from 2 words. Okay. So, and then, let's see. Went back a bit. Okay, so with GTID, it's a lot easier because you don't have to be so directional about it. But the worst case I just outlined, you would be rebuilding like that. So if databases are kept small, each one of these steps should take no more than about 2 hours. So let's say you have about a terabyte based on your transfer rates, your disks. So it's not that big of a disaster. It's not like Emily loses an entire weekend rebuilding cluster X. anyway, so data centers can die, and that's why we enforce planning for it. So cluster back to normal. In a real life story, in January, I got an alert that something was unreachable. And so I logged in, and it was indeed unreachable. Luckily, it was on the inactive side, so nothing really had to happen. There was just reduced availability, potentially. And I tried to log into the physical host. I couldn't get there. I tried to log into the control thing for the server, the rack itself, and nothing would work. The on-hands person sent a picture of the server, and things in the server had actually melted. Like there's plastic falling off of memory pieces. So it wasn't that big of a deal. That's the point. Like something that catastrophic was not a big deal. It was just a matter of having the server replaced and spinning things back up. It wasn't a catastrophe. Everything's been automated. We can just, as soon as it's ready, bring it back up.
You don't consider melting plastic a catastrophe. What do you consider?
I don't know. See, I don't have much stress. So, yeah, we still had 3 nodes to survive on, and that's better than a lot of jobs previously. So it's not such a big deal. Like if something were an extended outage, I might kind of think, maybe I want to redo the replication chain so that this is the most likely one to be strung off of this. So it's not very common. Things don't take that long. And so our failover utility, I will go in. Yep.
When your master failed, how do you take care of the latency, replication latency before you restore other master?
What do you mean?
So inside, in the previous scenario, you showed that the A side failed and you booted up B side as part of made it the read writer, right?
So we always only ever have one read-write node. We don't often have things reading from read-only replica. Is that, like, where's the latency that you're thinking coming? You're talking about the catching up to replication lag?
Like you write everything to the A side, right?
Yep.
And if the A side data center fails, right? So how does B side takes over before, what happens to transactions that are there on A side and not yet replicated to B side?
So let's say A side fails. It's just, they're down for the amount of time it takes somebody to run the failover tool.
But the transactions are already there that has been committed on A side, and they are not seen by B side.
It is asynchronous replication, yes.
And that's why I was wondering there would be a loss of transactions.
The applications that need that protection have it built in. So yeah, well, a lot of it is, not all of it is. So, I mean, there are applications that aren't just financial stuff. There are a lot of operations behind it. So if an application needs that kind of durability and consistency, they have checks internally. So.
Do you have a different architecture for those cases?
No.
So they replay those.
It's on the application to sort it out. So at the time we're on asynchronous replication. Maybe in years when we get to MySQL 8 and yeah, not there right now. So yeah, we get more in depth with our tool for failover directly after this presentation in Hill Country D. So I alluded to small database size being important for transfer and rebuild speed earlier. We like to keep things at a terabyte or smaller. And so applications are urged to begin sharding from the very beginning. So let's see. So let's pretend this is all for one application. They might end up with something like this. And you'll see some nodes are out and some things have been failed over. But we just keep scaling out for them. And the sharding solution is actually on them to choose because we don't know their data, we don't know their access patterns, so they're the best ones to choose. We will advise on a sharding solution, but we do advise, period, a sharding solution, period. Because if they grow too big, we can't maintain the same restore capability. So we keep adding clusters as they need, and ideally the app has isolated each cluster. And we scale, this is how we scale out. Not bigger hardware, not bigger databases, just more clusters. So remember the theme. Pebbles, not folders. What's that? What is the size of one cluster? The data stored is generally 1.2 terabytes, thereabouts. I think that's when it starts alerting to them well before that, but I will get into how we do our alerting, which kind of is a proactive. They can silence it if they want, but I don't recommend it. So anyway, smaller is always easier. It doesn't always work well. There was a phase when I had joined the company where there were a number of applications that hadn't really planned for sharding, and doing sharding after the fact was pretty hard. But we did it, and I don't advise it at all. So yeah, we just don't know the access patterns, so we can't take them to that level, but we have options available. So on to backups. So for Redis, we actually usually have Redis entirely in memory. And in that case, if we needed to make a backup, we could write a backup. But our disaster recovery is based on the topology, not on the backup in the case of Redis. And there are applications that do need persistence. They need that guarantee, and we can enable it. So it's usually in the form of AOF, but also sometimes RDB. Let's say I have to do something, and everything's memory resident, and I just want that extra safeguard. I might write an RDB really quick one-off just to have it there. And for MySQL, of course, the go-to for hot online backups. That's all we do. So we do a full daily on all of the inactive nodes, and actually I looked, that's not quite, every single gray node we seem to be doing a full daily backup on them. We encrypt it, we have it monitored, so we'll get paged at like 9 in the morning each day if any backups have failed, because they are so essential to protecting our stuff. And we have a Ruby script that wraps extra backup commands and sends information to the monitoring stack. And I mean, as you could see before, we do a lot of rebuilding and moving and shuffling. So we verify by rebuilding nodes and bringing them in. So this is part of our extra backup command. Of course, ulimit, umask, and capture the slave information and stream through XBStream, and we pipe it through PIG-Z to make it small. I've tried some other compression, and this just works well enough compared to the alternatives. And also GPG, so it gets encrypted, and we capture the entire backup, the MD5 of it, so we know that when the next step happens, if we reconstitute a backup, that it's accurate. So we split it into 4 gig chunks. Another example of keeping things small. It's just easier to deal with a backup in 4 gig chunks than it is to deal with a terabyte backup being shipped. Okay. So on to access and security. Yes?
What was the reason you had to do backup on all slaves, basically?
We want it physically located in a location in the, so let me just go back to the topology. Okay. So let's say I need to rebuild this one. It's easiest to get it from the same data center. Or, yeah, so that's the theory. Most places, most options. Sometimes backups aren't good. Sometimes they fail. We want the most number of backups possible, except for the active node.
But do you have to keep them for a long time, or what is the retention for your backups?
We have a known retention policy within the company. So sometimes you get asked, like, do you have a backup from 3 years ago? I think I have fielded that question. They could have, that's proprietary. I mean, we can ship them to the cloud too. So it's the option that they have. So on to access and security. Let's see. So the basics of how we do things, which was covered in a previous talk about our TLS stuff, is that there is application specific access. So application foo can only access its clusters. Bar will never be able to get to foo. If bar wants foo's stuff, the standard answer is use the API for app, or app foo. It's just much more scalable. You don't have to worry about, let's say, the indexing changes on, or the schema itself changes on foo, and suddenly bar is expecting something. It's much easier just to provide it out of an API. So anyway, let's see. Okay, and everything is TLS at Square. So we just don't have passwords. Yeah, the one person that knows. Yeah, there's a cat reference. My cat's name is Finley. We use TLS with auth instead of password, and it's actually really simple. I had never used it at a previous job, but compared to having people share their passwords between team members, compared to just the overhead of dealing with password maintenance, it's far better. And yeah, Finley will only have access to, well, in this case, start out star. This is a generic command, just FYI. There is not a start out star with all privileges. It's a very privileged cat. So, let's see. So yeah, this was the talk that we just had on our system. So what we do is we have an automatic rotation of these certificates, just as best practices. It's just best practices for everything. The actual app users, the application, and the system level things like replication. And further, we have actual networked zones. So if something is within a certain class, it gets placed into a zone, that has no communication with the other zone. Yeah, that's another division. And then furthermore, let's say blue zone really needs some new hardware. I've just decommissioned a bunch of stuff in the red zone. It's not as simple as dropping red zone hardware into blue zone. There's an entire process for super secure reuse, maybe. In some cases, no reuse whatsoever, destroy. So that's another level of security that we maintain. Monitoring and alerting. I'm doing too badly. So the basic theory here is, I'm sure people have experienced having a really, back in the day, horrible Nagios alerting system, which all of the alerts are just flooding in constantly. They're meaningless. And you're getting notified for things that you absolutely can't handle. We divide our application hierarchy such that it's much more manageable. And we just basically use SignalFX for graphs. We use PagerDuty. It's good at what it does, the one thing it does, which is sending me a page and giving it to the right person. And let's see, we have our artisanal local and remote monitoring agents. Depending on what year you ask me, I might tell you we're using a different system, so it's not really relevant. But it's all very custom. And of course, we provide query metrics to our application users so that they have the tools that they need. They don't need to ask us, like, what's performing badly? They can take a look. That's a big, something that's really special about Square is that we give the power to our user base. We're not blockers. We're not the gatekeepers to anything. They have all of the information that they need. They have the tools that they need. They can do failovers. They can do online schema changes all without us. They're not waiting for us. I'll get into that in a bit. And the most basic check we do, and it's because we have such a simple topology, is that is the cluster looking like it should? Is the SIP there? Is it up? Can I talk to it? Is that read-write? Is that read-only? Okay, cool. Replication looks good. I mean, that's the most basic check, and that goes to our team, the DBAs, and also backups, because, I mean, we're the ones using the backups that care about the backups. If a backup fails, the application owner doesn't need to know about it. We need to know about it. And replication lag, that's something I have no control over. I don't want to know that an application, well, a little bit. But let's say they're doing a long online schema change and they know things are just going to be bad for a while and they have raised the threshold of it to be very tolerant of replication lag. At 3 in the morning, I don't want to get paged for something. I have no idea what's going on. I don't want to go down that hunt of why. So they get that alert, not me. And they can choose to silence it if they want. And similarly, yeah, so everything's divided. Is it a database problem or is it an application problem? I don't need to know about application problems. There is nothing I can do. I don't even know what is hosted on these servers. So it's not me. But is the database okay? That's me. Oops. Whoops. Sorry. So let's see. Have I covered everything there? Yeah. Okay, so on to advice. This is the basic theme. So everything, keep it small, keep it simple. And pebbles, not boulders. Like I always hear my coworker who has a super deep voice saying, pebbles, not boulders. And that's just stuck. Like when I'm working on anything, and I'm looking at the architecture of how we do our operating system upgrades. Like every tiny little unit is just something that we can reuse a lot. It's easy to troubleshoot, and it's not like, oh, okay, is active. The check to see if the database is active, that failed. Okay, simple. It's not like something fails and you have to go on a hunt. Advice, the negative bits. Assume everything will fail. Architect around always assuming failure first. No manual processes. It was not a delight to run bash scripts. It was not to do operating system upgrades. It was not a delight to do Ruby scripts to provision that would inevitably fail. So we just automated it out, finally. No fancy replication chains. So I have worked in places that had very interesting replication chains, like so that something could be isolated from something, and then there are replication filters over here. That is really hard. That becomes a snowflake fast. So, and then coming into that company, you always have to ask somebody, and then maybe that person isn't there to explain it. So you have to kind of reverse engineer why. So just keep it simple, keep it standard. Just take a basic template and run with it and engineer the parts around that template. So no fleet-wide operations. Like, don't change everything at once. Do a small chunk. That's kind of obvious. And only alert DBAs on DBA issues. Don't alert them on application issues. And don't blindly trust new versions. We have a process where we vet in staging very slowly, and then we vet in production very slowly, especially for certain known issues like you can suspect that there's going to be a problem with the optimizer, so take it slowly. That is, you always have to be ready to fall back. And then obviously don't use MySQL as a queue or a cache. So I did work with Pim at a place where MySQL was literally used as a cache a lot. And it was awful. It was soul crushing to not be able to manage what was in that table. So it's kind of extreme soul crushing. And don't be a roadblock. Like, that is my happiest thing about my job right now, is that the users have tools. We have Shift, which is open sourced and getting a rewrite, which allows our users just to run online schema changes, and they have their own approval process. So they don't have to ask us to alter table, add index. Like, that's on them. It's on them to test. And yeah, and it also has some safeguards in it, because they don't need the access to do that if you put it out there. And then positive advice. Yes?
App users have been known that when you give them too much power, however, they tend to abuse it. Do you guys do any post-analysis? Like, you give them the ability to add indexes. Do you ever do any post-analysis to check for duplicate indexes or unused indexes and just let them know?
I don't know if the page is still available. We did have something that did the PT, whatever that, yeah. It did a bunch of those best practice, like just scanning things, and we can do that on demand for them too. But yeah, there was a thing that they could see if they needed to fix things. So test HA situations in production. You should do that. You need to know how your production traffic is going to handle failing over from side to side or DC to DC. Shard from the very beginning. Like, it seems like it's difficult, but if you build a culture of sharding from the beginning and give them the information that they need, it works. Plus, they know the repercussions of not sharding from the beginning, which is, oh, you need that when. It's going to be like a day before I can restore that, and then replication is going to be checked. You know, you don't want to have that conversation. And I have probably said that in the last year, at least once. Yeah, limit the shard sizes. So we base our 1 terabyte on how long it takes us to transfer it between data centers. So that is where we get that number. It's not trivial. And if somebody asks, why are you telling me that there's a problem? Why am I getting an alert that it's, you know, approaching 1 terabyte? Well, it's because you need high availability. And in order to do that, we need to restore your stuff within a certain amount of time. Yeah, keep the clusters small. Automate everything. I make mistakes all the time. It's caught by automation. And let's see. The most basic level of monitoring is that everything is as you expect it to be. So if you're doing not much monitoring, is it up? Is it correct? And it's very easy if you have a standard topology, because you don't have to guess what is correct for that particular system. And provide some sort of query metrics. PMM is a great solution. Vivid Cortex is a great solution. You could use just about anything. Those are simple. And run PT table checksum frequently. So at many stages in our regular operations, we run PT table checksum. Over time, inconsistencies are almost guaranteed. It's better to know about them proactively. Okay, questions? Oh boy, Tom.
So we have the 4 hosts. Is the host that was in red, is that always doing all the reads and writes, or is like the
Yes.
always okay?
We do not split writes.
Well, no, I mean reads is more
Well, they can access the other nodes, but we don't provide an SLA guarantee on the other nodes because we're doing operations possibly. So let's say they have a random query they want to check. That's where they go.
Is there any requirements regarding the query journey from this shard to the other one? How do you deal with
That's
that?
up to them based on their sharding solution.
Oh, okay.
That's an application problem, not my problem, and that's a hard problem to solve, so it's good.
your multi-data centers, is it hot warm or is it hot hot?
Depends on the application, actually. There are actually some 2-node clusters that operate independently, same application, different data center. And they have their own sauce for how they go between them.
Do you have rules for how applications can be? Because you're pushing so much stuff off the application. So do you have like, do you put, so boundary constraints on them?
Constraints on applications,
Do you
I
rules
have,
in terms of the fancy stuff they can do?
no. I mean, they work for a financial services company. They're going to be conservative, probably. So, yes.
If everything's automated, what do you do?
Mostly cat pictures. No, just designing new stuff. It's pretty cool because I don't spend much time fixing things. I spend more time working on the future, which is a good place to be. Yes?
With manual sharding and limited shard size, how do you redistribute if you need to?
That is on the application again. So depending on their sharding solution, I think it's pretty easy with something like Vitesse. We also have libraries that they can use for sharding. So the answer is I don't know. It depends. Yeah, sometimes they'll start writing initially to 2 different tables or reading from 2 different, and then that gets moved to 2 different databases, 2 different servers, clusters, whatever. That's the worst possible solution. There are easier solutions.
So how do you handle the network failover like between the data center and at the same time in case if your primary dies, what do you do?
Okay, so if the primary dies, I'll get into this in the next session, which Brian ran out to set up for. Basically, we don't, our failover tool has a mode that is failover. So it doesn't even do any checks of the original stuff. It just says, I'm down, I need to be up because that is more important than anything right now. So don't do any sanity checks, kick me over, make it good. That's the theory. Yes?
I have a question about the storage.
Uh-huh.
What kind of storage, when you have that many duplicates of the data,
Yeah.
what kind of storage do you have on one of the servers?
RAID arrays. So,
You have RAID.
yeah.
Okay. And are they SSD? Know them? Are they?
Yes.
Yeah.
And we have some legacy machines that have fiber. Yeah. Okay, thank you.
Thank you.